Okay, welcome back, everybody. So I thought I would finish up in the first few minutes the last official things that are discussed in the textbook. So the way the textbook works is basically it gets you to exactly this point, the 18th century, and then it offers like a ton of like different selected topics. Most of the selected topics. I'm not really going to follow the textbook at all from here on. I'm just going to basically give kind of an overview of those three areas that you guys had mentioned, or according to the polls, everything was pretty much even. So geometry there's a nice segue here from this material that we're doing now to geometry. So that's what I'm going to start with, and then I'm going to talk about analysis and set theory and foundation stuff after that, and that will be it. So there's a little bit to tidy up with Laplace. So we were talking about Laplace at the end of class last time, and I had defined this Laplacian. So if I have a function, and you can define this whether it's a function of two variables or a function of three variables or even a function of n variables. It doesn't matter. You can define the Laplacian. So in the case of a function of two variables, the Laplacian of f is its double x partial, okay, plus its double y partial. In the case of a function of three variables, the Laplacian of that function is its pure x, y, and z second order partials. Okay, and similarly for a function of n variables, you can define the Laplacian of a function to be, f sub x, x sub 1, x sub 1, x sub 2, x sub 2, and so on. So I'm using this notation here in case you've never seen this notation of using subscripts to denote derivatives. If we used, so if I have a function of multiple variables, the partial derivative of that function, say with respect to x, can be written like this. This is adapting Leibniz's notation to partial derivative. Why do we use this weird curly del symbol instead of d? Because it's supposed to indicate that because you have a function of more than one variable, there's not just one derivative of the first order, there's two. So there's the derivative of the first order with respect to the other variable. So if you've never had Calc 3, or if it's been a while since you've had Calc 3, you might have forgotten how this works exactly. And we can write this in shorthand. It's typically a lot more convenient to write this instead. So f sub x means the partial derivative with respect to x. F sub y means partial derivative with respect to y. And so f sub xx is the second order partial. It's d2f dx squared, right? Where instead of having d here, we have this del thing. So that's what's meant by this, just in case there's some confusion over the notation. Okay, and so the Laplacian can be also given a really, really nice description. It's the trace of the Hessian matrix. Of f. So if you don't know what the Hessian matrix of f is, Hessian matrix is the matrix that contains all of the second order partial derivatives of f. So if you put that in as a matrix, if f is nice, that matrix is symmetric, which means if you write it out as matrix rows and columns, you can flip it across the diagonal and it's the same matrix. And so the diagonal itself, if you sum all of the diagonal entries of a matrix, that's called the trace of a matrix. These are the diagonal entries of the Hessian. So if you write out the Hessian matrix of a function, say of three variables, what it would look like is you'd have f sub xx, f sub yy, and f sub zz on the diagonal here. And so like here might be like f sub xy, and here's f sub xz, right? And here would be, say, so here's f sub yx, here's f sub zx, and so on. Well, I might as well fill it out now that I've filled it out all this way. So this is f sub zy, and this would be f sub yz. Yeah. So there. This is Hess f. So this is the Hessian matrix of F, and so the Laplacian is the sum, or it's the sum of these diagonal entries. Okay. There is yet another way of thinking about this. This is also the divergence of the gradient. Okay, so if you recall your vector calculus at the end of Calc 3, this is a divergence of the gradient of F. Okay. So a number of ways of thinking about this. So anyway, Laplace was kind of the first to really study this quantity a lot, and so he defined, or he studied functions satisfying this condition, and thus it's known as Laplace's equation. So Laplace's equation is a partial differential equation because it's a differential equation involving partial derivatives. And in a course on partial differential equations, this is typically the first partial differential equation, or PDE, that you discuss. Or it's one of the early ones, anyway. So functions that satisfy this, so functions satisfying Laplace's equation, are called harmonic functions. So functions that satisfy this, f is called harmonic. It's a harmonic function. And so the study of harmonic functions is a subfield of analysis that has, there's a lot of applied math that is related to, or not related, it's entirely dependent on this. So these harmonic functions are important in signal processing and all kinds of analytic applications. So anyway, so harmonic functions occur all over the place, and they are defined as being solutions to Laplace's equation. Okay. This operator can also be used to define. So Laplace's equation is kind of the first of the holy trinity of PDEs when you're first starting out your study of PDEs. So there's a couple others. There's the heat equation. So you usually begin by discussing the heat equation as you want to solve a PDE that looks like this for U, which is going to tell me my heat at some point. And usually you start out on a region, we'll call it omega. So we have a region, omega. This region has a boundary that we write del omega here. This is the boundary. And so this is a 2D region, we'll say. And so the 2D heat equation would look like this, since the Laplacian is written in this way. And so you have a function u that is a function of two space variables and one time variable. And so the heat equation is the derivative with respect to time is equal to the Laplacian of u. Okay, so x and y are space variables. They're describing, where you are on this boundary, and t is describing the time. Okay, and so this is an equation that describes heat. It describes heat at, on some boundary, or on, not just on the boundary, but on some region. Usually subject to some boundary conditions. I won't get into that too much. So when you're studying classical PDEs, this is kind of one of the starting points, and you'll have some simple boundary conditions, and you'll be asked to solve for this u function. Of course, sometimes this isn't even introduced necessarily as the heat equation, because this exact same equation doesn't care whether the quantity that you're solving for is describing, say, the distribution of heat. It just cares that you're describing distribution of something, right, that behaves like heat. So it's not just heat here, it's also diffusion more generally. And so this is also sometimes called the diffusion equation, because it's also describing that. Okay. To cap off the holy trinity of PDEs, There's the wave equation, which looks superficially similar to the heat equation. Okay. Okay. And so the wave equation is describing, well, exactly what it sounds like. Okay. A wave. All right. So these are examples of PDEs. And the study of PDEs kind of, I would say that they kind of had their starting place with Laplace. Not entirely. There are some earlier mathematicians that did a little bit of work on them, but Laplace did a ton of work on PDEs. So in fact, this is where you may have heard the philosophical problem called Laplace's demon. And so the reason for Laplace's demon being named for Laplace is exactly this problem of determinism. So this is kind of a philosophy of science issue, or almost like a metaphysical problem, which is, so Laplace had written this celestial mechanics, and Laplace had done a lot of work on PDEs. And so Laplace set forth this idea, this question of, suppose that you knew all of the PDEs that governed everything in the universe, right? So basically, assume that everything in the universe can be described in the language of PDEs. That's actually not that crazy of an assumption. I mean, that is exactly how we tend to try to categorize and describe these things. So assume that we can describe everything in the universe, and when we say everything, we mean basically give me, particle positions of all particles in all the universe, and maybe like, their initial velocities or something, and give me all of the PDEs that govern all of the interactions, all of the motions, everything. Right? Give me all those PDEs. And yeah, that's a really, really complicated system. But suppose that I'm just like really, really smart, right? And I can just, I have no problem like analyzing such a system. All right, so give me all those initial positions and velocities and all the initial data that I need, all the PDEs, and then let it go, right? So then start time. Laplace essentially, said that, well, like if that's the case, then basically it's completely determined, right? Like the system is completely determined from that initial data plus the PDEs that describe them, right? So this is known as Laplace's demon. And so physicists have a number of ways of answering this. So some of this, and you might have heard this, has to do with like information loss through maybe like something like a black hole. But there's a lot of weird things that go on here. And to be honest, most of the proposed solutions to Laplace's demon are not. They're not 100% convincing to me. I haven't heard any kind of updated arguments in the last 10 years or so, but a lot of the arguments they put forth are not super convincing. Some of the ones that I've heard in more like pop sci type places, and I'm not sure if the not convincing bit is on account of them trying to dumb it down a little bit, or if it's actually not that convincing of an argument in the first place. But anyway, I haven't looked into it. I'll leave that to you if you're interested. I'll write that out. Laplace's demon. It's a good thought experiment. Okay, I think that's pretty much all I want to say about Laplace. So Laplace is extremely important. A lot of times he's called the French Newton because of how important of a scientist he was, and he essentially, like Laplace's celestial mechanics was basically the cutting edge of cosmology until relativity, pretty much. So Laplace he was an important guy. Okay, one more mathematician that's listed in the textbook, and then we'll be done. And this provides a decent segue into what I was going to talk about next. So Legendre. So Legendre is primarily known for his contributions to number theory, but I've already mentioned his name before in the context of Euclid's parallel postulate. So he proved that the parallel postulate follows from the assumption that the plane contains real squares. Okay. I.e., quadrilaterals with four equal sides, each of whose angles is a right angle. Okay. So he also did work on the method of least squares. Have you ever heard of the method of least squares? So he did work on the method of least squares. And he did a ton of work in number theory. So in number theory, he defined a symbol that's named after him, and it's called the Legendre symbol. Okay, that's not maybe so creative of a name. So the Legendre symbol is the following. So let's take an integer and a prime p, and let's take the integer such that it's not divisible by p. So let n be an integer, and let p be a prime that doesn't divide n. Okay, so p does not divide n. All right, so n is not divisible by p. He defined the Legendre symbol in Legendre p, or n over p. Actually, how is this? I just taught a number theory course not too long ago. How was it? It's the most common way of saying this in words. Can't remember. So anyway, so in Legendre p. Actually, yeah. What is the? Now it's killing me. Now I gotta look it up. Like I said, I can't believe I just taught this course and didn't. Well, now I'm having issues finding this. Okay, well, it seems like there's not. I came up with a way of saying this, and I based this on what the textbook at the time was saying. But anyway, I can't remember. So anyway, well, you see the problem here, right? It's saying n over p, right? If you're not absolutely clear the context you're talking about, right? N over p always means a fraction, but that's not what this is, right? And it's almost similar to the binomial coefficient thing, which is, n choose p or n choose k the way it's written here, but there's a bar here. Right, I can't remember. Maybe I wrote n bar p. I can't remember exactly how I said it, but it doesn't matter. So what is this thing? So it's either 1 or -1. Okay, those are the only two options. And so the Legendre symbol, n over p, we'll say is equal to 1. Okay, if n has the form, if n is equal to k times p plus r squared, okay, where k and r are integers. So k and r are some integers. and the Legendre symbol n over p is equal to -1 if it is not of this form. Now, what does this say? So, really, the Legendre symbol, n over p, says whether or not n is a square mod p. Okay. And so you ask the question, is n a square mod p? The answer is yes if the Legendre symbol is 1, and the answer is no if the Legendre symbol is -1. Or I should reverse those. If the Legendre symbol is 1, then the answer to that question is yes. If the Legendre symbol is -1, the answer to that question is no. Okay. So Legendre symbol says whether or not n is a square mod p. Now, why am I bringing this up, since this seems kind of out of nowhere, and also I didn't really properly talk about modular arithmetic. It just kind of sort of came up when we talked about the Chinese remainder theorem. So what is the point? Well, Euler had conjectured a theorem that would later be called quadratic reciprocity. And what does quadratic reciprocity say? Quadratic reciprocity says that if you multiply the Legendre symbol of P and Q being distinct odd primes, so P and Q are distinct, that means they're different odd primes. Okay. Then if I multiply the Legendre symbols P over Q and Q over P, this is -1 to the, it's always either 1 or -1, right? Those are the only possible values a Legendre symbol can have. So multiplying two Legendre symbols, the only possible values they can have are 1 or -1. But it's -1 to the P -1 times Q -1 over 4. Okay, now Euler conjectured this. Okay, he couldn't prove it. Okay, Legendre proved some special cases of this. Okay, so he developed the Legendre symbol to discuss this. So Euler didn't have the Legendre symbol, and so he phrased this differently. The problem for him, or this theorem was stated differently. Legendre proved some special cases. So Euler couldn't prove anything here. He just basically had a heuristic that he was working on, that he felt like this was how it worked, but he couldn't prove it. Legendre proved some special cases. But not the theorem in entire generality. So this wasn't proven in generality until 1801 by Gauss. So in 1801, Gauss, so I'll go ahead and write his name, Carl Friedrich Gauss. Gauss was born in 1777 and died in 1855. Okay, so in 1801, Carl Friedrich Gauss proved that theorem that I wrote on the previous page, which is the law of quadratic reciprocity. Now, this is taken as a huge milestone in number theory, because before the number theory that kind of starts out of well, really, Legendre was kind of the first number theorist to move beyond, like far beyond, like Diophantus, like Diophantine type questions, right? So Fermat had done a little bit, but Legendre was kind of the first like person to actually have some big achievements, and this was carried on by Legendre, and then log quadratic reciprocity. This is taken in a lot of ways as a big turning point. So from this, you get a huge explosion of number theory. Number theory kind of takes off from this. It can be hard just looking at this statement to actually understand why this would be a big deal or why someone would even care. The biggest way I can try to explain this is basically this quadratic reciprocity says that whether P is a square mod Q has something to do with whether Q is a square mod P, and just thinking about it in the absolute most basic terms, there just does not seem to be any reason why that should be true. Like, it doesn't seem to be any connection between those things I just said. So the fact that this theorem is true is seen as really, really nice. And so the Legendre symbol is actually very easy to compute for a lot of those numbers. But I'm not going to go too far in that direction. I thought about giving you guys the option of number theory, but I had to, I had to cut some things. So that was it. So if you're interested in that type of thing, then I can talk more about it. So you can let me know. But anyway, this leads us to talk about Gauss. So Gauss proved this in 1801. Gauss would actually come up with many different proofs. I think like 5 or 6 different proofs for quadratic reciprocity over the remainder of his life. And this is a nice segue, whenever we talk about Gauss, this is a nice segue into my discussion of geometry and what occurs here, because we're now fast approaching the time when geometry is kind of turned on its head, or rather, mathematicians' eyes were opened as to what was really going on. And this opening, is not just, it doesn't just concern mathematicians in ivory tower doing their own thing, not worried about applications, but it would have been impossible to formulate relativity without non-Euclidean geometry. So like non-Euclidean geometry is taken as the foundation of relativity. You literally cannot have relativity stated in Euclidean terms. You have to have an understanding of Riemannian geometry. In fact, even semi-Riemannian geometry, slight generalization. These things had to be built up. And little known fact, it wasn't, relativity didn't come out of nowhere. In fact, Einstein wasn't even technically the first person to publish a paper on relativity, right? So the mathematician Poincaré, I think like 6 weeks prior to Einstein, had published basically a paper on relativity. When Einstein was doing his work, obviously Minkowski and Lorentz had already done a ton of work in the area, and that's why Einstein referenced them and Einstein used their results. So this is this is very much a thing that shows that even when non-Euclidean geometry was first discovered, it was kind of viewed as just a curiosity, or maybe just it was kind of interesting, but really it was only interesting to kind of to people that were just geometers and only worried about like purely the abstract. But this turned out to be mega useful. So Gauss is the big is kind of the big name associated with this, even though he technically didn't come up with non-Euclidean geometry. He didn't discover it. He claimed later that he had discovered it in his notes, and maybe he did. It's not totally impossible that he did, because he was definitely at the forefront of geometry. So definitely not impossible, but for whatever reason he just never published and didn't talk that much about it. So what was Gauss known for? When Gauss was I think when Gauss was only I think he was like a teenager. I think he was like 18 or something when he did this. So Gauss constructed a regular 17-gon using compass and straight edge only. So we're going back to our roots here. Gauss was actually the first to do this, right? So literally, he was the first since the ancient Greeks to construct a new one. Literally the first person since Euclid in the Elements to construct a new regular polygon that the Greeks had not constructed. Okay, so that's a big deal, and he was only a teenager when he did that. So while only a teen. He famously, supposedly, was given a task by his grade school teacher when he was really, really young. The teacher just wanted to give the students something to work on, wasn't that interested in teaching that day or whatever, and so I guess maybe Gauss in particular was really annoying with questions, and so the teacher told either Gauss or all of the students to sum all of the numbers from 1 to 100. And so Gauss, did the trick, which is if you try to sum all of the numbers from 1 to 100, it looks like this, right? And so, of course, if you notice that you can pair them all up, every time you pair them up in this way, they sum to 101, right? So 100 plus 1 is 101, 2 plus 99 is 101, and 3 plus 98 is 101. And of course you can do that in pairs. The question is, how many pairs do you have? What did Gauss discover? So Gauss had discovered that this was 100 times 101 over 2, or 50 times 101, so 5050. Okay. So this is the sum formula, right? It's usually one of the first things you prove when you do induction proofs. So the sum from, say, n equals 1 not to infinity, that would be bad. The sum from n equals 1 to k, okay, of n is k over k plus 1, or sorry, k times k plus 1 over 2. All right, this is like one of the shortcut sum formulas that you learn. Okay. So, Gauss supposedly basically, figured out this formula when he was, I don't know, some ridiculous low age, like he was either 3 or 5 or 6 or something, when he did this. So he was, like archetypal mathematical prodigy. Gauss had a ton of contributions, and I can't go through absolutely every single one of them. So I mentioned he was the first to prove the law of quadratic reciprocity that we mentioned before. So he did that in 1801. He did a ton of important work in geometry. So Gauss pioneered a ton of very important work in geometry. Lots to do with, so specifically, the geometry of curves and surfaces. Okay. But to do geometry of curves and surfaces in the way that Gauss was doing it, this was not the Greek way. The Greek way had no notion of a derivative, right? The Greeks had no idea what a derivative was. They had no idea what an integral was. They had no idea about any of these quantities, right? And so what you had was geometry in the way of the Greeks, but you're adding in calculus, right? And of course, when I say calculus, I don't mean literally calc 1 and 2. I mean calculus and everything that comes from it. So all of the analysis of Laplace, all of the partial differential equations, everything. Okay, so calculus plus analysis in general. And so what we call this subject, this amalgamation of classical geometry together with calculus and just absolutely everything that that we know about these quantities, this is differential geometry. So Gauss was kind of the pioneer of differential geometry. And if you take Math 436, which I'm teaching in the fall, that is the differential geometry of curves and surfaces, and basically it traces through almost all of Gauss's work together with some stuff that was kind of cleaned up by some later mathematicians. Okay, so this is what Gauss was responsible for. Okay, it's why it's so funny that he did not like explicitly write out non-Euclidean geometry, because the work he did in differential geometry, it has it baked in the easiest possible ways. So he could have easily seen these examples, but for whatever reason, he didn't until it was done a little bit later, while he was alive. So he was alive while when non-Euclidean geometry was discovered. But it's interesting that he never explicitly wrote it out, even though it is implicitly in the work on differential geometry he did. So at the time, mathematicians were very confused over what it means to do geometry. Okay, and so the big central question is, what about geometry of, say, a surface? Okay, but that wasn't really just what they were thinking of, but let's say a surface. So what about geometry of a surface is inherent to the surface So this was called intrinsic geometry. Okay. And what is, or what should I say, what comes from the ambient space it sits in? And this was called extrinsic geometry. Okay, so it seems like a pretty natural question here. The idea being, like, I could take almost anything you can dream up. I could take, literally almost here's like a strip. Okay, consider this strip here as a surface sitting in space. And you might say, okay, what if I take the strip and I have it held like this, right? And I'm only thinking about like this piece of the strip, right? So you could talk about the geometry of that, right? And the strip itself has some geometric quantities and qualities. But what if I have it's the same strip, but it's sitting in space slightly differently, so, right? So what if I don't do anything crazy, I don't rip it or tear it or crease it, I just have it kind of bent like that, right? Well, it's the same strip, but it's embedded in the ambient space in a slightly different way. Okay, so the question is, how does that affect the geometry? How does that change what it is that's going on? That's one example of the sorts of questions that they were asking. Okay, and the thing that Gauss was able to say is that there's no such thing as intrinsic and extrinsic. There's just geometry. So Gauss was able to show that there is only intrinsic geometry. What does that mean? I.e., it doesn't matter how it sits in the space. Okay. It doesn't really matter how it sits in the space. So why is that important? that is important because it allows you to throw away the space that it sits in. Okay. And so when I think of, say, a sphere, I don't need to think of the sphere sitting in space, right, at the origin or wherever. I can just think about the sphere as being the only thing that exists in the universe. Okay. Now you might say, all right, what is the benefit to that? Well, on one hand, it shows that the space that it sits in doesn't actually matter. So there is geometry inherent to the sphere as it is defined, no need for the ambient space. And a great thing about this is that you immediately get non-Euclidean geometry right out of this with a careful reading of what's going on. We already saw that the geometry on a sphere is non-Euclidean, right? So you can, first of all, there's no such thing as parallel lines on the sphere, right? So every line, if extended on the sphere, right, it's a great circle, and all great circles intersect. So there's no such thing as parallel lines, so it's already different in that, like, you can't even state the parallel postulate, right, properly, because there's zero such lines, right? How many lines through, if we're using Playfair's axiom equivalent, it's if I have a line on the sphere, which is a great circle, and a point not on that great circle, how many lines through that other point are there that are parallel to the original line? Zero, because there are no parallel lines. So it fails the parallel postulate. It's non-Euclidean geometry. It's massively non-Euclidean, right? But, and even the ancients knew about spherical geometry, but because they viewed it as sitting inside space, they're like, oh, it's basically cheating, right? It's like cheating to use that as an example. So this fact that there's only intrinsic geometry, what's another way of saying that? Well, I can basically say that any question, so a question I have, say, about curvature of a surface, right? So again, how the surface curves in space, right? So the question is like, how can I measure that without talking about the space? Well, it turns out that I can talk about the curvature of a surface just from measuring angles and quantities on the surface itself. I don't need the ambient space to do that measurement. Okay. So I don't need the ambient space to tell me something about it, which is the point. Okay. This theorem is called the Theoremagregium. So this is what he proved, which is the remarkable theorem. It's remarkable because it's not really expected that this would be the case. It's actually kind of amazing that it works out to be like this. And so this led to just a massive eruption in progress in geometry. So this led to huge progress in geometry. The two mathematicians that I feel I must mention now are Janus Bolyai and Nikolai Lobachevsky. So let me get dates for them. So Janus Bolyai was a Hungarian mathematician. He was born in 1802 and died in 1860. So Janus Bolyai was a Hungarian mathematician, born in 1802, died in 1860. And he was born in 1792 and died in 1856. They independently discovered non-Euclidean geometry. So for historical reasons, as I said, spherical geometry, even though it had been known since ancient times, was never considered um, a non-Euclidean geometry, even though it very clearly is, because it was viewed as too weird. It was viewed as too weird, and it sat right there, like in space. So in some way, it was sitting inside a Euclidean space, and they did not understand the Theoremagregium and how you could talk about, the sphere and not include space. You don't need to refer to space whatsoever. So none of that was understood, of course, and so spherical geometry is not taken as an example of non-Euclidean geometry. And so when we talk about non-Euclidean geometry, we are looking for geometries that satisfy. So I'll put a little asterisk here, as I said. So this asterisk means geometries that satisfy all of Euclid's axioms but fail the parallel postulate. So every other postulate except the parallel postulate holds, but the parallel postulate doesn't hold. Okay. All right. The type of geometry that they discovered is called hyperbolic geometry. So Bolyai and Lobachevsky co-discovered independently hyperbolic geometry. Okay. Okay, so what is this discovery? There is a better description of the hyperbolic geometry that they came up with that is equivalent to what they did, that would later be done by Eugenio Beltrami. And maybe I'll go over a quick kind of example of that. But the idea, to give you something that is not exactly what they did, but it's equivalent to what they did. The idea is, what if I scale the usual length in the plane by a factor that depends on height? All right. So let's take the usual distance between 2 points, right? So I have distance between, we'll say point A and point B. All right. Now point A and point B have x and y coordinates, so A is, we'll say x1, x2, or sorry, x1, y1, and we'll say B is x2, y2. Okay, and so this is the distance between A and B. Okay. And the idea is that somehow we look at the distance here that we're going to compute, say between 2 points, and we scale depending on where we are here, right? So I'm going to be hand wavy a little bit here, but we'll say that instead of looking at distance, we take the distance and we scale it by the height, okay, y, of where we are, okay? Like that's the idea of what I'm doing here. Okay, so when I do that, of course, when I'm at height 0, I can't divide by 0, and so when we're at height 0, if I look at a point, right, and I think of it relative to its height, if I'm dividing by y here, that's dividing by 0, that's no good. So the x-axis is dashed because it's not included. Okay, so here's my x-axis. Here's my y-axis. Okay. What does this look like? Well, the idea is maybe I have a length between, say, 2 points here. And because I'm low, right, I'm close to 0, I'm dividing by a small number, which means I'm multiplying by a big number. So this length might be the same as the length up here that looks like this, right? So these two lengths would be the same, right? So if this is L1 and this is L2, maybe in this case L1 is equal to L2. These two lengths would be the same. Okay, so there's a way of doing this and we can be entirely consistent in how we do this, and it yields a type of geometry on the upper half plane. So this is called upper half plane. So this is the upper half plane model of hyperbolic geometry. This is probably the simplest way to describe it, and usually even in a course where this is done. So even if you take like Math 430, where near the end of the semester that's what is studied is hyperbolic geometry. This is exactly how it's developed. So how does this work? Well, the lines look like this. Lines are so these are actually not lines, okay? So these are not lines in hyperbolic geometry, right? We draw them, they look like lines to us, but in this geometry, they're not lines. What do lines look like? So what does a line mean, right? A line, a geodesic, okay, as it's called, is well, there's some complication here, but think about it as a length minimizing thing. Right? And so the reason why these are not lines is because they do not minimize the length, the distance between these 2 points. So they are not length minimizing curves, I should say. They're not distance minimizing curves. If you want to know what those things look like in this geometry, well, they look like one of 2 things. If the 2 points are vertical, one is directly above or below the other, the line that is unique, right? So it's non-Euclidean geometry, but it satisfies all the other postulates, which means 2 points determine a line. So if you give me 2 points in the upper half plane, there's a unique line between them. So for those 2 points that are vertical, that's the line. So this is an example of a line. What's the other type of example of a line? Semicircles with their center on the x-axis. So this line that I just drew would not be parallel to L, but it would be parallel to this one, right? So here's L2, here's L3. Okay, so L3 and L1, we'll say, intersect each other, but L2 and L3 don't. So L2 and L3 are parallel, L2 and L1 are parallel because they don't intersect. And now you see exactly the problem, right? So the parallel postulate fails. Right? If we use Playfair's axiom version of it, what would that say? Well, here is my parallel line, or here's my line, we'll say. Okay. Here's a point not on that line. How many lines can I draw through this point that are parallel to this line I started with? Infinitely many. There's one. There's one. There's one. There's one. All of those are parallel to this. So infinitely many points, infinitely many parallel lines through P. So infinitely many parallel lines to, we'll call this line L. To L through P. Okay. And now you're going to say, well, maybe you'll say, well, wait, that's cheating, right? Because you just changed what lines are, right? But did we? Right? Did we change what lines are? Well, how, right? How did we change what lines are? So it turns out that these lines are governed by equations. Okay, they're governed by equations that determine what the lines are for this geometry. Those equations are called the geodesic equations. Okay, they are in general differential equations. They can be really nasty. They can be really really horrible to look at. But here's an example of a simpler thing that pops out of it, right? So let's go back to Euclidean geometry. So what is my definition of a line? What is a line? Well, a line does not turn. Right? People would not have a problem with that. It's a path, right? It's a non-trivial path that doesn't turn. Huh. It doesn't turn. What does that mean? So if I have a function, say f of x, or we'll say, yeah, let's say that we have a function f of x that describes position. Okay. If it doesn't turn, what does this mean? It means that its second derivative is 0. Okay, so think about that from a physical point of view for a second. Its second derivative is 0. Okay, but using the fundamental theorem of calculus, if the second derivative of f is 0, I can integrate both sides with respect to x. By fundamental theorem of calculus, what do I get? If I integrate the second derivative of f with respect to x, then I get the first derivative of f with respect to x. This is equal to, when I integrate 0, I just get a constant, right? I'm going to call that m, right, where m is a constant. Okay, let's do it again. So here I get f of x, which tells me the position of this line. What's the integral of m dx? It's mx plus another constant, which I'll call b. Oh, wait. Right? This is my equation for a line. Right? This is just the equation of a line. And so we started with a description of line as being this path, right? If we think about it as a graph of a function such that its second derivative is 0. From that and from calculus, I get, oh, just the equation of a line. So if a function satisfies this, it's a line, right? And so, and vice versa, right? You can go the other way. You can say if I have any line, right? As long as if it's not a vertical line, then I have to, I have to do something funky because it's not the graph of a function, so I would have to alter it in a little bit. But if it's just a line that's not a vertical line, then this is exactly what the equation of a line looks like. All right, so this is what the equation of a line looks like, and I'm good to go. Okay. Well, what if I told you that the same equations, right, that determine that these are the lines in hyperbolic geometry, when you put them in Euclidean geometry, all the terms, all the nasty terms, so they're called Christoffel symbols, all these Christoffel symbols vanish. They all go to 0, or they're all equal to 0. And what you're left with is the differential equation f double prime is equal to 0. It's just that you don't see all of that complication happening in Euclidean space because Euclidean space is flat. And when you are dealing with a flat space, all those weird, funky terms that would show up here don't. Okay, they don't show up. And so that is why these are lines, and we didn't really change the rule at all. Okay, so these are absolutely lines for hyperbolic geometry. Okay, so I'll talk a little bit more about Gauss and especially what his student Riemann did next time, and then we'll kind of be just going through at a nice pace, trying to pick all of the good stuff. So anyway, I will see you all next time.